In this video, we will see how to calculate the channel capacity for some symmetric channels. In general, the calculation of the channel capacity can be difficult because we have a constraint maximization problem. We need to maximize the mutual information between the input and the output of the digital channel, and the maximization is done over the input distribution. Therefore, the unknowns are the probabilities of the input symbols. In this case, the probabilities of these four symbols that are denoted by pi for the probability of p and the probability of xi, to simplify the notation. Now it is necessary to evaluate the mutual information. For instance, between the difference with the difference between the entropy of the output and the conditional entropy of the output given the input. This is one of the usual expressions that can be used to obtain the mutual information. Now, the conditional entropy of the output given the input can be obtained by averaging the entropy of y for every possible symbol x. If we transmit x0, the output is binary, because in this case we have y0 with probability 1 minus epsilon and y1 with probability epsilon. Therefore, the entropy is the entropy of a binary random variable when one of the elements has probability epsilon, the other one has probability 1 minus epsilon. This is the binary entropy of argument epsilon. If we transmit x1, now in the output we have three possible symbols: y0 with probability epsilon, like y2, that is received with the same probability, and y1 is received with probability 1 minus 2 times epsilon. Therefore, we have here two terms related with a probability epsilon, 2 times minus 2 times epsilon logarithm of epsilon. Here we have the term associated to the probability 1 minus epsilon, minus this probability times this times the logarithm of this probability. It is straightforward to see that okay, we can rearrange these terms to get a more compact expression, but in any case, it's relatively simple to obtain this conditional entropy. Now, it is straightforward to see that for x equal to x2, we have more or less the same situation that we had for x1. Three symbols, one of them with probability 1 minus 2 epsilon, in this case y2, and two of them with probability epsilon. But the entropy is the same one that the entropy of y when x was equal to x1. And something similar happens for x3, because when we transmit x3, we have two possible symbols in the output, y2 and y3. One of them is with probability epsilon, the other one is with probability 1 minus epsilon, similarly to the situation with x0, and the entropy is the same one. Therefore, now we can obtain the conditional entropy of the output given the input by averaging these four entropies for I given each value of x. And we have this very simple result. To obtain the entropy of the output, it is necessary to compute the probability of y0, y1, y2, and y3. We need the distribution of the output. It is straightforward to obtain these probabilities using the trellis representation of the channel. And once that we have these four probabilities, we have the addition of minus each probability times the logarithm of the corresponding probability. And we get straightforwardly this expression here. And now here we have a reminder of the previous expression for the conditional entropy of y given x. Now we have an expression for the mutual information between x and y, but this expression depends on four parameters: the probabilities of x0, x1, x2, and x3. And in general, it can be difficult to find a solution for the maximum of this expression. However, if we consider the symmetry of the channel, we can see that the dependence of these expressions with respect to x0 is the same one than with respect to x3, and the dependence with respect to x1 is exactly the same one that we have for x2. In fact, if we change p3 by p0 and p2 by p1, we get exactly the same expressions. Taking this into account, now we can parameterize the four probabilities using a single parameter, taking into account that the maximum of the mutual information will happen for the same value of the probability of x0 and x3 and for the same values of the probabilities of x1 and x2. So the first two probabilities are parameterized, for instance, as p halves, and the other two probabilities are parameterized as 1 minus p divided by 2. In this case, the four probabilities add up to 1. Once that the four probabilities have been parameterized using a single parameter, the rest of the process is just simple maths. Now it's possible to write the probabilities of the output for every symbol as expressions of a single parameter p, and the entropy will depend on a single parameter p. Maybe we can get by some operations a more compact expression, for instance, in terms of the binary entropy, but what is important is that we have an expression that depends on a single parameter. The same thing happens for the conditional entropy of the output given the input. We have a single parameter p in these expressions. Now, if we have the mutual information written as a function of a single parameter, to obtain the maximum of this function with respect to the parameter, we can equate to 0 the partial derivative of the mutual information with respect to this parameter. It's straightforward to obtain this derivative, and then the last step is to solve these equations for p. And this parameter p now provides the four probabilities for the input symbols, because we have parameterized the four probabilities in terms of a single parameter. And with this single parameter p, now we can compute the channel capacity, and we can get the input distribution that maximizes the mutual information between the input and the output. Depending on the channel, maybe this solution is not unique. The distribution that we have here maybe is not unique, but at least we have a possible solution that is valid in most of the cases.